Hey everybody, my name is John Beverly. We'll be talking about basic formal ontology today. To give you an idea of the structure of the talk. Here. Two parts. Part one, I'm going to go through part one pretty quickly because I know you guys are already experts on BFO. But I'm going to give you a little refresher, what it does and why. Tell you what BFO implementations are, which is what I've been working on for the past semester. And tell you about some of my work, mine and Fumiyaki's work on the BFO first order logic, that's FOL, first order logic update. Then in part two, I'm going to tell you what I think is probably the more interesting thing that I've been doing, which is not exactly updating the implementation, but translating everything into a theorem prover and proving cool stuff about BFO, some of the consequences. I'll give you several examples depending on the time, and talk about the upshot and future work for that. So, everything you thought you knew about BFO. It's probably right. Well, let me tell you a little more. So, basic formal ontology, based on a theory developed by Smith and Grennan. I think I'm pronouncing his name right. It's an upper level domain neutral ontology. Basically, you get a smaller or sub ontologies, low level ontologies, material ontologies. You put those into this bigger upper level framework and kind of translate the domain level stuff into this upper level stuff. That way, all of these domain level ontologies can kind of talk to each other. This solves things like data silo problems, makes it queryable, and as long as it's formulated with rigor and according to the principles laid down by Smith and Grennan, turns out you don't run into these weird mistakes that previous ontological ventures had encountered, as Smith rightly points out. Here's the hierarchy. Isn't it pretty? These all should be familiar, things like entities, these types, or these categories, continuous occurrence. I'm going to be talking about several of these. It's good to have this here, though, in case you have any questions, because I'm going to be talking somewhere about at this level of depth later with some of the examples I use. If you have any questions or want to see exactly, look at how they relate to each other, just ask. I'll come back. Slide 6. BFO, used by many people. This is from Infamous. I have the website here. I could not capture all of the various projects that are using BFO because the list was quite long. As you can see, it cuts up here. If you want more information, go to this website. See all of the various people that are using BFO, right? All these ontologies talking to one another, whatnot. They're able to. Now, BFO, basic formal ontologies, has versions. It's people discuss and dispute and debate over what should be in the upper level ontology, and because of this, there have been significant changes. Right now, we're in BFO 2.0. It's the second version. This has been on the table since about 2011. I'm not sure, but it itself has undergone lots of changes too, which we'll talk about in just a minute. Now, an implementation of this, of the theory, the BFO theory, is going to be realization of a technical specification as a program or a software component. You see things like here are going to be implementations. OWL. This is used in web development. Protege. This is an implementation of BFO. Cliff. This is a common logic interface format. This is like a very abstract lingua franca for lots of different logics. We can talk to each other. This has a lot of potential, still being developed right now. First order logic. These are actually go pretty closely together. This is commonly used in it's very theorem prover friendly in a way that Cliff at the moment is not, which I've talked a little bit more about in the future. Anyway, these are implementations of the BFO specification. Now, this BFO version 2 implementation, this requires, when these new versions come out, they're going to require new updating of the specifications. So that requires updating to say, if we're thinking about these, OWL, Cliff, full. At the end of summer 2012, several individuals who worked in BFO projects, they got together to present updated implementations. And so what they did, they produced in 2012 a Cliff version of BFO 2 and a first order logic axiomatization version in LaTeX, input and output. Okay, this is useful. The LaTeX itself is converted in this nice, look at that font, it's so pretty. In a nice way that you could see and view in a PDF. Just see the logic. I'll show you in a minute. Like this. So here's an example. You can pull this straight out of the text file. Perusing it, you'll find full axioms. So for all x, if x is a continuant, then it's an entity. Right? So it's something you would find in the BFO reference manual, the specification, or at least this kind of reasoning, and this would be the way you captured it with first order logic. Good. Right. Here's an example. I'm an entity. Well, look, the axioms are changing. They often change. Like I said, lots of disputes, lots of changes too, even the versions. So we needed to, so lots of changes since 2012. We needed to update it. This young man, this aspiring magician, and this young man, also an aspiring magician. What's up, Flemmy? We took the task to updating this. I'm happy to report that it's been done. Let me say that one more time. The file's been updated. The text file's updated. The Cliff file's updated. This works. Happy to report it's been accomplished. Now, that's probably the least interesting stuff. I know I went through that quickly. It's done, so I don't care so much about it. If you have any questions, go ahead and ask before I move on to what I find the most interesting thing. I know that part of the grade is going to be like asking questions, good questions, a fortiori questions. So I'm going to need questions, so this is kind of like the roll the dice, and we'll see if it's a good question, because it's better than no question.
Are you asking us for questions?
That's what I'm doing.
Okay,
right?
so
clear pause for questions.
All right. So I'll ask one. What's an implementation?
Realization of a technical specification. Reference manual is a program or software component, not software.
All right.
Does that make? Did I move through that too quickly?
Yeah.
I get super excited, man. Sorry. Is that? Yeah.
Okay, from your first several pages, I can feel you love logic. I appreciate that. So my question is, using two sentences to describe what's the major difference between AI perspective of logic and philosophy perspective of logic? What's the major idea difference between these two perspectives?
Well, one, the AI tends to be more focused on things like complexity and computational power, and then on the other side, if you're doing philosophy, tend to think more about the expressivity of your logic, how it can be implemented in philosophical theories, like metaphysical programs, things like that. I would say that's not two sentences. Complexity versus like expressive power.
Also, the logic came first.
Oh, well, sure. Historically, the logic came first.
I mean, the philosophical.
Well, the philosophical logic came first. Does that answer your question? Yeah.
Yeah. Did you use only first order logic, and did you have to use second order logic?
First order. Sticking with the first order. Yeah.
Or the formalization of the BFO. That's something I'm trying to understand. It's
So-
part of my work too.
So you discuss this. You say that you're still within the realm of first order logic, but you're quantifying over relations.
So
For
we
relations and
quantify both over instances and over universals.
And over universals. So I've
And
just
that way we can simulate having quantification of the predicate,
Mhm.
but without treating the predicates as predicates. We treat them as constant terms.
yeah.
And then we have relations like is that or part of,
Mhm.
which link predicates.
Yes.
But in fact, they link names to universals.
Yes. So we're still right in the
Still
realm of
first
first order. Yeah. I had to think a lot about that too. It wasn't clear to me, but yeah.
So then would it seem like BFO, how friendly is BFO to modal logic?
That doesn't have no modal aspect, modal implementation.
Well, this is
Uh,
the nearest we get to anything.
I wouldn't call that. Yeah, it's as close as it's going to get, but you're not going to have like sentential operators like that to quantify over worlds or models like with worlds like that. Right. I'm going to move on to the interesting stuff. Oh wait, it's too interesting. Okay. So, Dr. Diaper in 2013, he advised moving to a user-friendly automated theorem prover, or various user-friendly theorem provers, such as things like Prover 9. This is just from a slide he used. And the idea is if you axiomatize BFO, and you basically plug it into a prover and you see what falls out. It's a nice way to prove theorems, because I don't know if you guys have done a lot of logic, let me skip that one. But doing a lot of first order stuff is boring. I mean, like after a while, you just get tired of proving the same thing. It's like typing "Hello World" when you're learning a language or something. Come on. I had a linear algebra professor who once in our class, like the first day, he said, "Hey, show of hands, how many of you can compute large numbers in your head?" And like half the class, this is a big auditorium, half the class raised their hand, and he goes, "Don't do that. That's silly. Computers can do that for you. Why would you do that?" And he's right, because the class was about proving things, doing things that computers couldn't do. We're doing like more advanced topics, so you shouldn't be wasting your mental energy. Similarly, I don't want to waste my mental energy trying to prove whether or not located in at is transitive. I just let a computer do that for me. Again, yeah, don't waste time when a computer can do it for you. Nevertheless, theorem provers can help you just like a calculator might, but it's still going to require some kind of creativity. Theorem provers don't. If you put something in a theorem prover and you say, what falls out, it's going to be there for a while. You have enough axioms. So instead, you have to query, you have to ask, like, is this a theorem? Can you prove this? What do you think? Right. You gotta know what to look for. So there's a creative aspect. A lot of theorem provers require modularization, they will require modularization with an axiomatic system the size of BFO. It's very big. Comparatively speaking, it's a pretty big axiom system. Modularization is going to be taking some subset of all the axioms, plugging it in somewhere, proving things about that subset, maybe combining it with others. I'm going to give you several examples in just a minute of how we do that, or how I do that. So Dr. Dykert did point out when he was discussing the prover, automated theorem prover stuff, that there's no way to easily translate Cliff or these LaTeX files into a language that common automated theorem provers can use. And he's right. There are people working on those projects, but they're not, there's no immediate translation yet. But Prover 9's language is close enough to the text or common logic as it was already specified or implemented that could be easily translated by me. So I went ahead and did that. Now Prover 9 can read all the axioms. I'll show you how. Incidentally, this is me before I started. It's ready to go. And this is me after. It took a while. It wasn't exactly easy, but it's done. This is just a snapshot of my folder. I modularized. This is what I mean by modularized. I took, continuant axioms. And it's a very brute force method I used here. Anything that mentioned continuant is in this file. Anything that mentioned generically dependent continuant is file. It's going to be a lot of overlap. Need to, clean some of that stuff up. But right now, that's how they're modularized. All right. Now you can easily just input these into Prover 9. We're going to walk through Prover 9 in just a second. That's the automated theorem prover I used for this. Here's the nice, cool snapshot of the user interface. But I want to back up just slightly. I want to show you how it works before we start doing some of the real BFO examples. All right. What do you think? Yeah? You set the premises in the GUI, in the graphical user interface, and then you set a goal. This is what I was talking about a minute ago about being creative. You got to have some kind of creativity to figure out what the goal is. This took me a long time to figure out. I was like, is that the goal I should be looking for? Yeah. This is just modus ponens. Here's the proof. The sentential logic modus ponens resolution proof. Prover 9 works by resolution. That is, it clausifies things, or clausifies premises. And what that means, it puts them in conjunctive normal form. A conjunctive normal form is a form, it's a series of conjunctions, or it's a series of disjuncts conjunctively joined together with negations. So if P then Q, logically equivalent to not P or Q, clausifies in that way. And then it negates the goal, tries to find a contradiction. Proof by rejecting it. This is a very common way that automated theorem provers work. This is actually general. Like it's computationally fine. It can solve a lot of really big problems very quickly. And it was, again, also one of the ones that Dykert advised using, and Fabian too. He said, if we could do this, yeah, so you should. We'll try another example. This one using first order logic. We've got here a disjunctive syllogism with quantifiers, right? This is how you would input it, all x, all y. And the way the language works is I don't have to put premises or parentheses around it, so you can see. And then it not exists some px. Okay? So everything's px or gx. Not the case there exists a px. And then I put, prove this, that there exists a gx. Just jump to syllogism, right? So the way prover 9 works is it negates that somewhere here. It's going to end up negating that there exists a g, and it proves a contradiction, so you infer that so it says not exist a g, shows a contradiction, infers there's a g. All right, now it's time to put away the toys, though. Lots of this is going to be like screenshots of my computer. I tried to get rid of, if you see anything that looks, John, what is that? I tried to get rid of all that stuff. Here's the GUI. Open the input files. You generate axioms, and the generation is just opening the input files. I've already done the work of like putting them into a file, and you see here, these should look pretty familiar. These are some of the things you would see in a BFO specification in the prover 9 notation, or the prover 9 language. And I also have the citation number commented out so you can see where to look. Yeah. Remember this one? I'm an entity, right? And this is the continua file. So everything that mentions continuous is going to be in there. Let's look at some more examples, or actual examples from BFO. So S depends on, specifically dependence. It's kind of like existential dependence. Specified in BFO 2.0 holds between A's and B's at a time, such that they share no parts. If B exists, C must exist, and B is neither a boundary nor a site. It's similar, like I said, similar to existential dependence. Here's some examples: pain, specifically depending on an organism, and gait, specifically depending on a walk. Intuitively, this is going to be an irreflexive relation. The reason is because continuants are parts of themselves. One of the aspects of BFO. So every continuant is a continuant part of itself. And because of that, since S dependence is something where they share, or a relation where the entities share no parts in common, you'll be able to infer that specific dependence is not reflexive. So nothing S depends on itself, because since every continuant is part of itself, that's a part in common with itself, right? Is that reasoning? Okay. Just trying to pump the intuitions here that this should be a plausible thing to prove. And it is. It's provable. Just plug it in and prove it. That specifically dependent continuant, or specific depends on, is irreflexive. That's what I call proof. Let's look at material entities now. Material entities is the continuants. These are, things with material or matter as parts. Plausibly, if an entity has a continuant part, it's a material. Oh crap! I've been talking too long. I didn't realize. I'm gonna kind of. You get the general strategy. I'm gonna kind of show you some of the things I prove rather than walking through all the details. So this is what I'm proving. If an entity has a continuant part that is a material entity, then that thing's a continuant. Here's the input file that you would see. Voila, theorem is proved. Proven on up. This is a trivial. You can prove very trivial axioms too. If a continuant part of a material entity at a time, or an object is, then an object is an independent continuant. This actually just falls out of independent continuants objects being material entities and being independent continuants. It is trivial, and the proof is pretty trivial too. A less trivial thing is process profile of relation, showing that if something is a process profile of something else, then there's another thing that is a continuant part of the y, and it's not identical to x. This straight out of the BFO specifications should be something that's provable, and it is. It just takes a long time. I actually cut it off. It was a very long proof. It took a lot. But I thought it wasn't going to prove it for a minute. It just kept running, and I was like, no.
What are the numbers down the left?
The numbers are some of the premises that are being used.
Oh,
the numbers in the modularized
so it's
file.
not hours of computer.
No, gosh, no. My computer wouldn't run that long. I don't think it ever has. Okay, so I proved some just kind of interesting theorems. What else do I have? It's useful for proving the theorems, but it's likely more useful for reworking the way the axioms are formulated currently. Because they may lead to undesirable consequences. So rather than there's one way you might approach capture or constructing BFO 2, and that's like top down. You come with your axioms on the table, and you're like, I guess this is what would fall out of these. Let's put them on the table. Another way you might, or in supplement to that, go is say, here, let's let a theorem prover pull out all the consequences of these axioms, and if we get anything we don't want, figure out which axioms did what, and go back and rework it. I think that's the better way to go about it. I don't have that kind of foresight, sorry. So, Prover 9 lets us do that. I'm going to use process profile as an example because it's kind of underdeveloped, and you can prove that something, if it's a process profile, is both an occurrent and a continuant. Here's the proof. It's pretty long too, but it's an unfortunate consequence. You don't want process profile to be both a continuant and an occurrent. You like it? The proof will set you free? I told him beforehand. I was like, I got some pretty good puns here. Oh, blasphemy. Yeah, the lesson to learn, given the resolution method, we can identify problematic premises. And since they were all laid out, the premises, we can just look to see which ones cause the damage, make adjustments where needed. This allows us to work backwards and noting those consequences. Finding all future work, finding all my mistakes. I made a lot. I just tell you now, preface paradox. Prove independence of axioms using this modularization method, which is something you could just, you could do manually, but nobody wants to. Parsimoniously redefine predicates in terms of the fewest primitives, and then ensure alignment with philosophical motivations. Those are things to do in the future that I think Prover 9 and these automated theorem provers in general would be helpful in pursuing. Starting from the Prover network here. Questions?
All right, so we have 3 minutes for questions.
Is the Prover 9 easy for the beginner?
Yeah, absolutely. That's one of the benefits of it. So, there are other theorem provers, things that can, let's say, read Cliff directly. Like Hex is one, but it's got a steep learning curve. This Prover 9, you could just go home and I'll send you the axiom. You can start playing with it now. Like, use not a learning curve. Just plug it in and say, can you prove that? Boom.
More importantly, easy for you?
Mm-hmm.
Oh, good.